Okay, so we are now ready to state the main theorem of this section. Okay, so the theorem has been stated in the textbook. Okay, so we call it the representation theorem of trigonometric Fourier series. Right, so let f be a periodic function with a period 2 pi. Okay, and piecewise continuous on a finite cost interval from minus pi to pi. Right. We further we assume that f has a left-hand derivative and a right-hand derivative at each point of the cost interval from minus pi to pi. Then the trigonometric Fourier series A0 plus summation n from 1 to infinity an cosine nx plus b sub n sine nx, okay, generated by f converges to f of x, right, except for all x in this finite cost interval, except at the point x where f is discontinuous. Right? And there means a point x where f is discontinuous. Well, the sum of the theories is the average. 1/2 of fx minus plus f of x plus. Right, so it's the average of the left hand and the right hand limits. Of the function f at x. Okay. All right. So so this theorem answered the two problems we raised before. For the convergence problem, or the convergence problem, the answer is yes. If f is a periodic function with a period to pi and piecewise continuous, so we state sufficient conditions on the periodic function f, okay, such that the answer to the convergence problem is always yes. Right, so the first thing is that it is continuous, it's piecewise continuous on minus pi to pi. Okay, and the second condition is that f has left hand derivative and right hand derivative, right, at each point of this finite closed interval. Now, this condition implies two things. The first thing is that f is absolutely integrable over this finite closed interval, okay? Because that is piecewise continuous, okay? As we mentioned last Tuesday, okay? So that, and because that f is absolutely integrable, so that it can generate the corresponding trigonometric Fourier series, right? So this Fourier series exists. You can construct this Fourier series. Okay, and the piecewise continuity by its definition, which implies that f has the left hand and the right hand limit, right, for all x in this finite closed interval. Okay. So, as you can see from the definition of piecewise continuous functions, you know that this fact 1 and 2. And with this second implication, together with this condition that f has a left hand derivative and a right hand derivative, then we know that this trigonometric Fourier series converge to this quantity for every x in the finite closed interval. Okay, converges by actually this is from Dini's theorem, I think. So, yep, and the remark, okay, and the remark after the Dini's theorem. So that, and so you can see if x, right, if the function f is continuous at x, then we know these two limits is equal to f of x, right? So they will be the same and equal to f of x. So half of them becomes to the f of x. Okay, right? So we know that this trigonometric Fourier series will converge to f of x, right? For every point x where f is continuous. So of course, the exception is that it will not converge to f of x when f of x is discontinuous. But anyway, in that case, this convergence probably always true, right? As has been guaranteed by Dini's theorem. Okay. So actually, we prove this fundamental theorem. Okay. So, any questions? Okay, so the proof, please see the lecture notes. Okay. Right. All right, so I just state the basic idea of the proof already. Okay. Okay, and the detail, I think you can look over the detailed proof in the lecture notes. Right, so let's see an example. Oh, by the way, any questions about the statements of this representation theorem? Okay, so we really prove this theorem, right? All right, so we have considered a rectangular web before, right? So let me address this example again. Okay, with the fundamental period 2 pi before. Okay, and this example we have is here. Okay. And the function value at minus pi at 0, well, can be arbitrarily assigned. Okay, so in here, I didn't specify the value of the function f at minus pi and at 0. Okay. All right, so let me say that where f can be arbitrarily defined at x equal to 0 pi. Okay, and we have shown that the trigonometric Fourier series generated by f, okay, alright, is we have shown that before. Is here. pi here, and sine 2k minus 1 x. Right. Okay, now we look at the figure of this periodic rectangular wave. So we see that okay. So you can see that this periodic rectangular wave is piecewise continuous, because when you look at the function from minus pi to pi, you can see that this function, because they are constant, so this function is continuous in this subinterval, open subinterval, and continuous in this open subinterval. Okay, and so we have only to consider 3 points: minus pi, 0, and pi. Okay, and at minus pi, you can see the function has right-hand limit. Okay, it is constant. At x equals 0, at x equals 0, right? It has a left-hand limit. The left-hand limit of this function at 0 is minus 1. But the right-hand limit, right, one limit of this function f at x equals 0 is plus 1. Okay, so they are different, but f does have right-hand limits and the right-hand limits too. Now, how about at x equal to pi? It has right-hand limit, right? I'm sorry, left-hand limit, which is equal to 1. And because of periodicity, so of course, at pi, it has the right-hand limit. And this right-hand limit is equal to right-hand limit at minus pi by periodicity. Okay. So of course that since f(x) piecewise continuous, all right, minus pi and pi, and has how about the left-hand derivative? Because that in the open interval from minus pi to 0, the open interval is differentiable, and the derivative is 0 because it's constant. So this is differentiable at every point in between minus pi and pi. Okay. And when we have this differential, then the right-hand limit, the left-hand derivative and the right-hand derivative will be equal and equal to the derivative. Okay, so you have here. Okay, so I think f is absolutely integrable, right? It's absolutely integrable over minus pi and pi. And oops. Sorry. Has the left hand derivative and right hand derivative. Okay, and right hand derivative at every x in minus pi and pi. Okay, those four. And because, and since f of x is equal to minus 1, this interval, this open interval, f is differentiable minus pi to 0. Okay? So that the left hand derivative f prime x right hand derivative and the right hand derivative okay exists and equal to the derivative of f at each x in the open interval, because it's constant. Okay, so differentiable and the derivative is 0 for all x in this open interval. Okay, and similarly, f of x is equal to 1, the open interval 0 to pi. So f is differentiable 0 to pi, so that the same right? Now, so at these two open intervals, now the f of x has a left hand derivative and a right hand derivative already here. Now, so we have to check 2 points, right? So that 3 points, minus pi, 0, and pi. Okay? Now, the right hand derivative of f at x equal to minus pi, the right hand, right, at x equal to x here is limit, so f of minus pi plus is limit, okay, and t goes down, so it's f of minus pi plus t minus f of minus pi plus okay, and t here. But the right-hand limits of f at minus pi, which is minus 1, okay? Because that the right-hand limits of f at minus pi is minus 1. And f of minus pi plus t, okay, when t is small, the value is also a minus 1. So we have minus 1 minus 1 here. So the limit t goes down 0, which is 0. So we know that the right-hand derivative of f at this point is 0. Okay, and you can check the left hand and right hand derivatives of f at x equals 0 are. So now we check 0 minus, and 0 minus is limit t goes down to 0, f of 0 minus t, 0 minus and minus t, okay? So this is the left-hand derivative. The right-hand derivative at x equals 0, x here, plus, okay? And so you compute minus t here, and when t is small, so this is negative, and so what we have, so this is minus 1, and the left-hand limit of f at 0, the limit is 0, we know is minus 1 too, so minus 1, so again we get 0 and 0, so that this limit exists, which means that the left-hand derivative exists, which is equal to 0, and the right-hand derivative at t equal to at x equals 0. So this one is 1 minus 1, because the right-hand limit of f at 0 is 1, and this is t. So limit again 0 exists. So the last one is the left-hand limit of f, the left-hand derivative, I'm sorry, of f at x equal to pi, x here, sorry, I forget to put prime there. So f prime pi minus okay, and minus t here. So when t is small, so the function value is here. So this is 1 minus and 1. And the left-hand limit of the function f at pi is 1, 2. Right, so again, okay, so we check everything, right? Now we check everything. So that, and of course the right-hand limit of f at x equal to pi is the same as the right-hand limit, right, of f at x equal to minus pi, because of the periodicity of f. Okay, so we don't need to check them. All right, so we have that. Okay, so we conclude that f has a left-hand derivative and a right-hand derivatives, right, at each point in minus pi to pi. Okay, conclude that. Okay, and so by the representation theorem, okay, so that the periodic rectangular wave F satisfy these sufficient conditions. Okay. Okay, so by theorem 11.1.2, by the representation theorem, the trigonometric Fourier series, right? What is that? That one, summation k from 1 to infinity, 1 over 2k minus 1, 4, sorry, 2k minus 1 pi, and the sine 2k minus 1 pi, x. Okay. All right, so this trigonometric Fourier series generated by F, okay, converges, right? So has what? Has here that k equal to, so the sum sine, right, it's equal to f of x, okay, when x in R, but x not equal to say n pi for n 0, okay? And it is equal to because when x not equal to the integral multiple of pi, then f of x is continuous. Okay, so f of x actually is equal to this series sum. Okay, when x is not equal to the integral multiple of pi. But when x is equal to the integral of pi, then this series converges to this quantity. But if we look back to this rectangular wave, and then at each point, which is integral multiple of pi, okay, you can see that the left limiter and the right limiter is 1 and minus 1, right? Okay? And so the sum always is 0. Okay? So it is very interesting that so that we have so this is indeed this one is indeed equal to 0. Okay, since f of x minus equal to minus f of x plus for this point for all x pi. Okay, so we have this one. Okay, and so it gives us a formula, okay? Because when x is equal to n pi, then this zero sum is 0. And this is, actually this is obvious. Why? Because when x is an integral pi, then this is an integral pi. So sine function has 0 value. Okay? So you have 0, and the 0, everything together is 0. So this is actually, it is not hard to see, right? Not hard to see this. Okay? So when x is equal to an integral, a multiple pi, you actually get 0 value here, and this zero sum always 0. Always 0. Okay, but as you can see, we can arbitrarily assign a value, right? It's an integral multiple of pi. Okay. So you can see that f of x, if we define 0 value there, this is very common, right? So if f is defined to be zeros at those points, then we perfectly recover, right? Recover the periodic rectangular wave by this trigonometric series perfectly. Okay, so this is why this is the reason why when we describe periodic rectangular wave, we usually assign value at the discontinuity point to be 0. All right, so this is a very common way to assign value. Okay, for the periodic rectangular wave. Okay, and the strong reason is because in this case, then this is equal to f of x. Okay, so we perfectly represent the original rectangular wave by this trigonometric Fourier series. Okay, any questions? Yes, please. Yeah. No. Yeah, we apply the theorem. Yeah, because so to apply the theorem, we have to check these two sufficient conditions. We have to check that. Well, yeah, you can do that. But you have to take care every trigonometric Fourier series, right? Because for different f, you will have different trigonometric Fourier series, and you have to find what is the sum. It's not a simple job. I should say so. Even you have a very good tools learned from calculus, it's still not a simple job. But the theorem tells you that you don't need to do that. Once you check f satisfies these two conditions. So you can see I have invested a lot of time, right, to check both conditions. So first of all, that it's very easy to see that f is piecewise continuous, right? Just look at the figure. Figure is a good way to answer your question, okay? But the second one needs some elaboration here. Okay, even though this is a very simple example, I went through the detailed process for you. Okay, and this process is a common process that if you are given another possible f may be very complicated, but you can still use the idea, the procedure you learn here to solve your problem. So once you verify that the periodic function f satisfy both conditions, then by the theorem here, then we can have this kind of conclusion here. Okay. Okay. So any questions? All right. Okay, very good. So I think we can take a break earlier. Okay, so this take break up to 2:10. Okay. Okay. Right. So now we move on to the next section. We will consider a general case first, because in the first section we're considering periodic function with a period 2 pi. Okay, but actually the periodic function may have an arbitrary length of period, right? So it may not be just 2 pi. It can be period to be pi, or period is 1, or period is 100. An arbitrary positive number can be a period. This is the first thing we have to generalize the idea we learned in the previous section. And the second point in this part is about to consider the Fourier series such that the periodic function has additional property. For example, when the periodic function is an even function or an odd function. Okay, in that case, and then the trigonometric Fourier series may have some special form. Okay. Okay. So now, first of all, we consider a periodic function f with a period p equal to 2L. Okay, and which is piecewise continuous. Okay, minus L to L. Okay, and has a left hand and a right hand derivative. Okay, at every point or at each point. Okay, in minus L to L. Okay. Right, so the conditions is given to meet the requirement in this representation theorem. Okay, because in this theorem, that we consider functions with a period 2 pi, but then as well as see that we can generalize the application to other cases, for example, to periodic function with period 2L. Okay, and anyway, similarly we assume that this function is piecewise continuous on a range of length 2L, which is just a period, and also has left hand and right hand derivative at every point in this period time. Okay. Okay. So now our idea is to apply the representation theorem. Okay. So the general process is by changing variable. Okay. All right. So x is equal to p to pi and v. Right. So that this is become 2L to pi v and L divided by v. Right. So this is our change of variable. So the original function f of x now is just become 2f L divided by pi and v. Okay. All right, and so this is defined a function g of v, right? So this g of v becomes to a periodic function of v, okay, with a period 2 pi. Okay, so we turn this periodic function with a period 2 pi to be a periodic function with period 2 pi, a period 2L to a periodic function with period 2 pi. Okay, with 2 pi. And, all right, so GV and this satisfy the condition in theorem 11.1.2. Okay, so that f of x, this is f of pi v, which is gv. So gv can be written, okay, this one, and an and cosine and v plus bn sine v. Okay, so that, okay, it's for all x or v, right, where f or g is continuous. Okay, so we know that. Okay, and again, so we have this, and A0 plus summation cosine mv plus bn sine mv, right, equal to g v mass plus g v plus. Okay, and this is actually equal to the corresponding this is equal to f x minus plus g v plus okay, for x, right, v, where f g is discontinuous. Okay? And remember, we have the correspondence here, right? Once we have a V, we have a X. Or when we have a X, we have a V. So they can, they have a relationship here by this change of variable formula. Okay. And now, note that now this is called alright, now where A0, so A0 is 1 over 2 pi, and GV dV, okay? Now, but, okay, but GV actually is equal to f of L pi V dV, okay? Because GV by definition is this one, okay? But by the change of variable, okay, now because of x, we define x is equal to, so that dx is equal to L pi dv. Okay, so now we have 2 pi here, and this is f of x, and that, okay. So let's see that pi minus pi of L pi v, and here L pi dv. Now, so here we have times pi L here. Okay? Yes? Oh. Yeah, x is the value for f, and v is the variable for g function. Yep. Because for some v, right? For example, for all v such that g is continuous, right? This is the same for all x where f is continuous. Yeah. No. Yeah. It's not a function. It's the same. X corresponding to the function f, v corresponding to the function g, right? Yeah. Okay. It's a common practice in writing. Sure? I'm sorry. Now we will understand each other. Okay. All right. And so here we have 1 over 2L. Okay. And by the change of variable. Okay. So when v is minus pi and pi, then the x becomes minus L to L. All right. And this is f of x, and you have dx. Okay. So you see A0 it can be evaluated by the integration of the original periodic function over one period, right? From minus L to L, and divided by one period term. Any questions for the change of variable? And how about an? Again, an is 1 over pi, from minus pi to pi, and gv. and cosine NV and dV here. Okay, and once again, we have to do the change of variable, so that we have pi divided by L, pi minus pi, f of v, and the cosine, and NV. So v is, what is v? In this time, v becomes 2 pi Lx, okay? And dV, okay, here. Maybe at this moment, I just still write an MV, okay? At this moment, everything still V. All right, and then we do the change of variable here. So this is 1 over L, and now we change to x, right? When we use the x, then cosine and pi Lx here, okay, and the dx, and integration limits become minus L to L. Okay, how about Bn? Sine NV dV here, and then once again, pi divided by L, sine NV, L divided by pi dV. Okay, and again, 1 over L, L minus L, f of x, sine, and pi divided by Lx and dx. Okay? Yes. A0 plus AN cosine and pi divided by L x plus Bn sine and pi divided by Lx. Okay, let's. So this is called the trigonometric Fourier series, okay, generated by f, okay? So this is the and it's obviously can see that it obviously can see that this function, this is, if converged, is indeed a periodic function with a period 2L. Okay, a period 2L here. And this trigonometric Fourier series converges and A is 0. Is equal to f of x if for all x, right? Well, so for all x in R, well, fx continuous, right? And is equal to the average of the left-hand limits and the right-hand limits, right? When for all point x, where fx discontinuous. Okay. Okay, so this is the general formula, all right? And the application of the representation theorem to an arbitrary periodic function with a period 2L, okay, which has two conditions stated here, that the function f is piecewise continuous on a period of time and has a left hand and right hand derivatives at every point in one period of time. Any questions? Any questions? All right. So if no questions, we will consider a special case of periodic function. fx an even function. We consider two special cases. All right, okay. The first case is that fx an even function. F is an even functions on R, i.e. f of minus x is equal to f of x for all x in R. All right. In this case, okay, in this case, we look at Bn 1 over L. Okay, we look at here. Now this is an even function. This is an odd function. This is even. This is an odd. So the multiplication becomes to an odd function. Okay, an odd function. As an odd function, the integral from minus L to L is become to L to 0. Do you need me to explain why it's 0? Okay, good. Thank you. All right, so it's 0 here. And the trigonometric Fourier series generated by f becomes to here a0 plus summation n from 1 to infinity an cosine n pi divided by Lx. Okay? So you have only cosine terms. Okay. Well, we know the an come to so a0 is 1 over 2L and an is 1 over L minus L to L f of x cosine n pi Lx and the dx for all n greater than or equal to 1. Okay. Okay, so this is the first special case when the periodic function is an even function. Okay. Now the other special case is when the periodic function is an odd function. F is an odd function on R, i.e. f of minus x is equal to f of over x for all x in R. Okay, now in this case, we have, so we look at a constant a0. Okay. Now because the integrand is an odd function, so this integral is equal to 0. Okay, so a0 is 0. And how about an? Now, this is an odd function. Cosine is an even function, so the product is an odd function. All right? So as an odd function, this integral is 0. Okay. So that the trigonometric Fourier series generated by f x equal to bn sine n pi divided by Lx, right, with bn is equal to 1 over L minus L to L f of x sine n pi divided by Lx dx for all n 1. Okay, so we have that. And we have to give a remark. For an odd periodic function. Okay? For an odd periodic function. Okay, we have f of with period with a period 2L, we have C f of minus L, okay, is equal to minus FL because it's odd, but this is also equal to f of L, right? So this is from the periodicity. This is from the oddness. Okay? So from the oddness, we have this one, minus FL. But from periodicity, F minus L is equal to F of L. So what happened? This is implies FL is equal to 0. Okay, and is equal to F of minus L. Okay? So this is a must. So if a periodic function, which is an odd function, then you should have this. So so if you consider the periodic function on a period interval from minus L to L, then at the boundary point minus L and L, the function value should be 0. It should be 0. Okay. And corresponding to this trigonometric Fourier series generated by L, you see when x is equal to L or minus L, this is 0. Okay, because this is become to an indigo pi, right? For example, when x is minus L, this is minus n pi, and so sine minus n pi is 0. So the value always is 0. So you have correspondence. So this is not a coincidence. It's a must. Okay? It is a must. Okay. And now I state a theorem in the textbook, which will be used later, called linearity of Fourier series expansion. Okay, so let F1 and F2 be two absolutely integrable functions. The two periodic function. I'm sorry, periodic functions with a period, say 2L. Okay, and absolutely integrable over minus L to L. Okay, so that we have F1, F2. Okay, then let A0 plus summation n from 1 to infinity an cosine n pi Lx plus Bn cosine n pi of Lx and A0 prime plus summation n1 n prime cosine n pi divided by Lx plus Bn prime sine n pi divided by Lx. Okay, B the trigonometric Fourier series okay, generated by F1 and F2 respectively, right? So of course we can generate trigonometric Fourier series because F1 and F2 are assumed to be absolutely integrable. Okay, so we can have that. Now, for any alpha 1, alpha 2 in C, so if alpha 1, alpha 2 are to any R or C, can be real numbers or complex numbers. Okay. The linear combination alpha 1 F1 plus alpha 2 F2 of F1 and F2, okay, is absolutely integrable over, it's a periodic function with a period 2L and absolutely integrable. Okay. Furthermore, okay, the trigonometric Fourier series A0 double prime plus summation n from 1 to infinity an double prime cosine n pi divided by Lx plus Bn double prime sine n pi by Lx. Okay, so the trigonometric Fourier series generated by this linear combination has the following property. Has A0 equal to, whereas AN equal to alpha 1, AN double prime, you have alpha 1 AN plus alpha 2 AN prime. For all n greater than 0, and the Bn double prime is alpha 1, Bn plus alpha 2, Bn prime for all. Okay. This is called the linearity of Fourier series expansion. Okay. So if we have respective two absolutely integrable periodic function with period 2 pi here, okay, in this condition. Okay, and then when we do the linear combination of these two periodic functions, then this linear combination is a periodic function, with period 2 pi the same as both of them. And also absolutely integrable. Oh, I forgot to say over minus L to L. Yeah, I'm sorry, I forgot this one. And furthermore, the trigonometric Fourier series, so that this linear combination can generate, right? Because it is absolutely integrable, right? So it can generate a trigonometric Fourier series here. And then the corresponding coefficients here, for example, A0 double prime, all right, it can be obtained directly from the coefficient here and there. So this is alpha 1 with the same combination coefficient. So alpha 1 AN and alpha 2 AN prime, okay, for n from 0, 1, 2, 3, etc. And for B, we have the similar formula. Okay, so this is called the linearity of Fourier series expansion. Okay, any questions about the statement? Yes? Well, if, okay, this condition is sufficient to guarantee that we can generate a Fourier trigonometric Fourier series. Okay. Okay. Without that, then it's not guaranteed to obtain this one. Okay. Okay, so the proof, first of all, we should show that this one is absolutely integrable over one period of time. All right, so okay, I think the first quiz problem last Monday, right? Is about the vector space concept, right? Is that right? The first question, right? Yeah. So periodic function with the same period, right? They form a vector space. Okay. But well, okay. So we check, we let g of x to be alpha 1 f of x plus alpha 2 f1 f2 of x for x in R. First of all, right, we define this function as g. And so that g of x plus L to L is alpha 1, f1, x plus 2l, plus alpha 2, f2, x plus 2l. Now, because f1 and f2 are periodic function with a period 2l, so this is an x plus alpha 2, f2x. Okay, and then we have g of x for all x in R. So this is implied as g is a periodic function, right, with a period 2l. Okay, this is the first thing we can check. And now we check the absolute value and integrate over L from minus L to L. And this is alpha 1, f1 of x plus alpha 2, f2x, and dx. All right, and by triangle inequality, we know this is equal to alpha 1 absolute value, f1x plus alpha 2, f2x. Okay? So the integrand here, this integrand is less than or equal to this integrand. And this is 1. Okay? Now, because f1 is absolutely integrable over this interval, and f sub 2 is also absolutely integrable. So this integral is finite, this integral is finite, so the sum is also finite. So this is implies that g is absolutely integrable over minus L to L. Okay, so now we have proof that g of this linear combination is a periodic function is superior to L and is absolutely integrable over this finite cost interval from minus L to L. And so that we can generate so the trigonometric Fourier series, right, generated by G is here, except an a0 double prime plus summation n from 1 to infinity a n double prime cosine n pi divided by Lx plus bn double prime sine n pi divided by Lx. Okay, with that an a0 double prime, which is 1 over 2 L, integrate from minus L to L, and the g of x dx. Okay, this one. All right, and this is 1 over 2 L. And we do a substitution, alpha 1 f1 of x plus alpha 2 f2 of x dx. Now, by linearity of definite integral, so we have alpha 1 and 1 over 2 L minus L to L, f1 over x dx plus 1, this one, plus alpha 2 to L, f2 x dx. Okay, this one. And so this is alpha 1 a0 plus alpha 2 a0 prime. We have that. So this is from linearity, by the linearity of definite integral. Okay, we learned from calculus. And similarly, an double prime is here. Okay, and again, okay, so that this is alpha 1. Oh. Okay, again, by linearity of definite integrals, we have alpha 1. Alpha 2. So this is alpha 1 an plus alpha 2 an prime. Alright, and lastly for Bn double prime. For Bn double prime, okay, so that alpha 1 Bn plus alpha 2 Bn prime. Alright, so this complete the proof. Any questions? All right, so no question. Now, up to now, we consider periodic function. A periodic function is a function defined on the whole real line, right? Because it repeats itself. Okay, but in many situations, we should consider a function defined only a finite interval. Okay? For example, defined on an interval from 0 to L, for example, right? All right, so this is the topic, okay? Okay, so the question is how can we represent, how can we represent a function defined on the interval from 0 to L, okay, by trigonometric series. Right. At the beginning, you may think, but why do we relate such a function with trigonometric series? Because in our previous discussion, we use trigonometric Fourier series to represent periodic function, and periodic should be a function defined on the whole real line. Okay, but now we have only a function defined on a finite interval, specifically say from 0 to L. Okay, any finite interval can, by using the shifting property, right? You can shift to 0 and L. Okay, all right, by time shifting. Right. So, and how? But we will try, because we learn a lot of, right? Especially the representation theorem for periodic function, all right? And it gives us exciting result, right? So can we do that, all right? And so that it's possible, all right? So this is the next topic we have to deal with in these sections. It's about so-called half-range expansion. But I have to stop here, and we will have an additional supplemental lecture on the coming Saturday. The reason is because that we have two festivals, right? Coming soon. The first festival is about Mid-Autumn Festival, right? Beginning, I think, September 29th, right? And the second festival is about the National Day Festival, right? Okay, so that we will, especially in the National Day Festival, it's just Tuesday, so we have no class, so we have to have a supplemental lecture, and so I will record a lecture, all right? A lecture in the morning of the coming Saturday. And I will ask the TA to send you a link. Actually, we will put the recording in my YouTube channel, right? So just right after the recording, you can see that. So at least after in the afternoon, all right, just by the noon, maybe by the noon of the Saturday, you are able to watch the video recording. All right, you can, and you have to learn that, because that is in the mainstream of our lectures. Right? Okay. So I will possibly see you in the air, right, on Saturday. Right? Yeah.
Can be very quick.
Okay.
I'll talk about it. So